When we think about what makes our digital world tick, we usually think of complex algorithms or massive AI. But what if I told you that almost all of it is built on one of the simplest ideas in computer science? Today, we're talking about the array, the unsung hero, the absolute bedrock of how computers organize information.
I mean, think about it. How can your phone just flick through thousands of photos with zero lag? How does a spreadsheet recalculate a million cells in the blink of an eye? It honestly feels like magic, but it's not. It's just a really, really clever design.
And that incredible speed, that feeling of instant access, it all boils down to one simple yet incredibly powerful idea. So let's dive in and see how it works. Okay, to really get this, we're not going to start with code. We're going to start with something much simpler. Just picture a long row of numbered mailboxes, all lined up perfectly. This simple analogy is pretty much all you need to understand the heart of an array.
So here's the textbook definition. An array is a fixed-size container for a sequence of items. The two words to latch onto there are fixed size, meaning it doesn't just grow on its own, and index, which is just the fancy word for the number on each mailbox, its address. So these mailboxes have a few strict rules. First, it's a collection. Second, all the items inside have to be the same type. You can't mix letters and packages. Every mailbox gets a unique number, its index. And here's the kicker, and this is super important in programming. The numbering always starts at 0. So the first mailbox is actually mailbox number 0.
All right, so we get the mailbox idea. It's an organized list. But what makes it so mind-blowingly fast? Well, the array has a secret superpower. And it's not about the software. It's actually a secret that lives deep down in the computer's hardware.
And this is it. This is the secret sauce, contiguous memory. It sounds technical, but the idea is simple, and it's what gives the array its incredible edge.
So what does contiguous memory actually mean? It means when you ask for an array, the computer finds one single, continuous, unbroken slab of memory to put it in. All the mailboxes are physically right next to each other. There are no gaps, no detours. It's one solid block.
And that physical layout, that's everything. How does having everything side by side translate into instantly finding any single item, whether you want the 5th one or the 5 millionth one?
Well, here's the real magic trick. The computer doesn't search for an item in an array. It never has to look through the mailboxes one by one. Instead, it does something way faster. It just calculates the exact address.
It does it with this simple bit of math. The computer knows exactly where the row of mailboxes starts. That's the base address. And it knows how big each mailbox is. So if you ask for, say, item 500, it just multiplies 500 by the size of one item and adds that to the starting address. Boom! It doesn't search, it just jumps directly to the right spot. In computer science, we have a name for this, O of 1, or constant time. This is the holy grail. It means that the time it takes to get to an item is constant. It takes the same tiny amount of time whether your array has 10 items or 10 times billion items. It's always just one simple calculation away. And there's more. This physical layout has another amazing side effect. Because everything is stored together, when the CPU goes to grab one item, it's smart. It says, hey, you'll probably want the next few items too, and it pulls a whole chunk into a super fast little bit of memory called the cache. This is called cache locality, and it's the reason why looping through an array is one of the fastest things a computer can possibly do.
Okay, so we've been thinking about a single straight line of mailboxes. But what if you need something more complex, like a grid or a table? Well, this is where we get into the idea of dimensions. A one-dimensional or 1D array, that's our simple row of mailboxes. You just need one number to find something. But a two-dimensional or 2D array is basically an array of arrays. Think of a spreadsheet or a chessboard. Now you need two numbers to find a cell, its row and its column.
Now for those of you who want to go a little deeper, here's a fun fact. That 2D grid is just a convenient illusion for us humans. Deep down in the computer's memory, it's still just one long, flat, unbroken line of data. The computer just lays out the first row, then the second row right after it, and so on.
But no hero is perfect. The array's design gives it that incredible superpower of instant access, but it also comes with some pretty significant weaknesses. So let's talk about the trade-offs, or what we call the operational cost.
Think of this table as the array's report card. For access, it gets an A+. That's our O1 magic. But for searching for a specific value, well, in the worst case, you have to look at every single item, so that's slow, or ON. But here's its real kryptonite, insertion and deletion. If you want to add a new item at the very beginning, you have to physically shift every other item one spot to the right to make room. That is painfully slow.
So, this all leads us to the great trade-off in programming, knowing its strengths and its kryptonite. When do you actually choose the array to be the hero of your program? Well, you reach for an array when speed is king and your data is pretty stable. It is the perfect choice when you know roughly how many items you're going to have up front and you're not going to be adding and removing things all the time. Think about data that doesn't change. The months of the year, the pixels on your screen, the seats in a movie theater, all perfect use cases for an array. And this slide right here, this is one of the most fundamental trade-offs in all of computer science. The array gives you lightning-fast access, but is slow to modify. And then you have other data structures, like a linked list, which is the complete opposite. It's slow to find things, but it can add or remove items in an instant. And what's really cool is that the array's weaknesses didn't hold us back. They actually spurred incredible innovation. Smart programmers invented all sorts of new structures, like dynamic arrays or hash tables, specifically to get around the array's limitations. But guess what? Almost all of them are still built on top of the array's powerful foundation of contiguous memory.
So it all comes back to that simple trade-off. Do you need fast access or do you need fast changes? Now that you understand this, I want you to start looking for it. When you're scrolling through a feed and it's buttery smooth, you're probably seeing the power of an array. When you add a song to a playlist instantly, you might be seeing a different choice at play. Once you see it, you'll start to see this fundamental design choice everywhere.